So today we're going to look at image processing using the MNIST dataset and using neural networks and Keras. So a lot of new stuff today, including the fact that we're going to switch development environments to Colab from Google. So you need to go to colab.research.google.com and then upload this R file. Once you've done that, you need to go to set runtime and change the runtime to include R and T4 GPU. Okay, so this is the runtime, and now you need to change the runtime type. Okay, you need to make sure that it's R, so it should not be Python, it should be R. And then the hardware accelerator should be T4 GPU. T4 GPU. Okay. Now, we're just going to check the version so that we all have the same version. And then we need to install Keras, which takes a little bit of time to run. So what is Keras? So Keras is a very sophisticated neural network package that's used for deep learning. Okay, it's built on top of the TensorFlow package. So this is much more sophisticated than the neural net package that we have been using so far. And one of the things that it allows us to do is to define the neural net layer by layer. So it gives us an extraordinary amount of control. Okay, so here's the MNIST dataset. The MNIST dataset is a set of handwritten digits, and so we're going to try to predict what digit is in each image. Each image is 28 by 28 pixels. Now, one difference here is that MNIST already comes with a training and test sets defined. So we don't need to create a data partition. We don't need to do anything sophisticated. We just need to grab those data sets. And here's how big they are. So there are 60,000 images in the training set, and there are 10,000 images in the testing set, and they're 28 by 28 pixels. So let's just take a look at one of those images. So this is image number 3300, which looks like an 8, and in fact, it is an 8. So you can show the class by running ytrain 3300. And then here we can plot 25 images. So you can see how these handwritten images look like. And our goal in training this neural network is that we look at one of these images and we correctly classify it. So presumably the second one is a 0, then 4, then 1, then 9. Okay, so the very first thing that we need to do is that we need to convert the two-dimensional array, which is 28 by 28 pixels, into a one-dimensional array to feed it into the neural network. So this is called flattening. It's just a little utility, very simple, straightforward thing. The next thing we're going to do is we're going to create categories because this is the type that it needs to be in order for the neural network to run. And now we get to the definition of the neural network. Okay, so we have a set of layers here. So here's a layer, here's a layer, here's a layer, here's a layer. Okay, so this is by far the biggest neural network that we've created so far. So what is the first layer? The first layer is a densely connected layer. It has 256 units. It's using ReLU activation. And then this is just saying that there are 784 pixels coming in, right? So that's the input layer, okay? And then the next layer is one that we haven't seen, which is a dropout. So this is a type of regularization. It will drop 25% of the neurons during training so that they won't get updated. And then we have another layer that's 128, and then another layer that's 64. And then finally, we have this softmax layer at the end, which is going to do the categorization. So why is it 10? Because there are 10 different digits. And so each of those output neurons corresponds to one of those digits. 1, 2, 3, 4, 5, 6, 7, 8. Right? Actually, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay? And if we run this, we see how many parameters we have. So we have 242,000 parameters. Okay? So the biggest model that we've created so far. And you should be able to calculate how these parameters are arrived at. Okay, so how do we arrive at this? Well, so it's 256 neurons. Each one of them is fully connected because it's densely connected. There are 784 input neurons. So 784 times 256, that's the number of weights. And then plus the number of biases. So there are 256 biases since there are 256 neurons. And that gives you the number 200,960. So you should be able to do that for all of these other parameters as well. So like this last one is easy. there are 64 units. 64 units going in. There are 10 output units. That's 640 plus 10 in the bias, so 650. Okay, that one's easy to do. Okay. So here we compile the model. So here's the loss that we're going to be using. This is the error. This is what we're trying to minimize. We use this optimizer called Atom. So this is the backpropagation version, and we care about accuracy. And now we're going to train the model for 5 epochs. So here's the number of epochs. The batch size is how frequently we update the neural network. So every 128 images, we update the neural network. And then we're going to split out validation set, 15%. Okay, so this is 15% of the training set. So we've just run it, and we get this parameter called history out of it, okay, which tells us what the final epoch, the 5th epoch. So the accuracy is 97%. The validation accuracy is 97.7%, even better, somewhat weirdly. And then here we see the history. And so here's for every epoch, 1, 2, 3, 4, 5. Here's what the validation accuracy is. Here's what the training set accuracy is. So as we would expect, the validation accuracy is slightly less than the training accuracy, but no evidence here that we are overfitting. So if we wanted to improve this, we could increase the number of epochs. And then the final thing we want to do is we want to run this on the testing set. We want to run this model on the testing set. And we get an accuracy of 98%. Okay? And so that's what we want to do.